In section 6.1, we're going to work on solving linear systems by graphing. That is our learning objective, and you're going to find that a lot of these sections, the learning objective and the name of the section are the same thing. What we want to understand in terms of vocabulary is what is a system of linear equations, what is a solution of a system of linear equations, and what is a consistent independent system. So this is sort of vocabulary from this section, and let's take a look. So when you talk about a system of linear equations, which is typically just called a linear system, it has two or more linear equations that have the same variables, and this is what it might look like. And when you talk about a solution of a system of linear equations, there are three different ways this can play out. Typically, if the two lines intersect, they intersect in a point, and that point is the solution of the linear system. So the solution will be an ordered pair with an x-coordinate and a y-coordinate. On the other hand, there are two special circumstances that might occur when you're working with a linear system. I might have parallel lines, and parallel lines will never meet, and so they would have no solution. And sometimes when you have the two equations, they're actually equivalent equations. And when you actually go to graph them, you find that the two lines are actually equivalent equations and they make one line. And in that case, we have an infinite number of solutions. Okay, so there are three different ways it can work out. If the lines intersect, and what that looks like is they have different slopes. They will intersect in a single point, and your solution will be the x and y coordinates of that point. When the lines are parallel lines, that's going to be same slope, but different y-intercepts. Then you're going to have no solution. And when they're actually the same line, you're going to have the same slope and the same y-intercept. Then you're going to have an infinite number of solutions. Okay, so this is all the different ways that finding the solution of a linear system could play out. So one way to go about doing this is to graph them, right? So I can graph the lines and find the point where they intersect. And you can see these lines intersect at 1, 2, 3 for the x-coordinate and 1, 2 for the y-coordinate. Okay, and once I've sort of graphed them and thought, oh, well, maybe they fit there, I think this is the solution, because sometimes it looks a little crazy or not exact. If I want to check the point, I plug the x and the y into my other function, my other equations in place of x and y. Okay, and if I get true statements, then it is indeed a solution. So the first thing I'm going to do is I'm going to take 3 and 2. 3 plus 2 is equal to 5. 5 is indeed equal to 5, so it works in the first equation. And then I'll look at it in the second equation. Negative 2 times 3 plus 2 equals negative 4. Well, this is negative 6 plus 2 equals negative 4. And indeed, negative 4 is equal to negative 4. So again, I got a true statement. This is indeed the solution of this linear system. Okay, so when we're talking about a linear system that has, and this is important, exactly one solution, it's called a consistent independent system. So going back to the slide I started with, this one here is a consistent independent system. These others are not. Okay, so a linear system that has exactly one solution is a consistent independent system because the lines are distinctly different, they're independent, and they intersect. which is consistency. So what we're going to work on is solving those, but then also working with the other type of scenarios as well. So if I want to solve by graphing, the first thing I would do is graph both equations. Then I would estimate the coordinates of the point of intersection and then check the coordinates algebraically like I just did to test to see if they are indeed a solution. So let's take a look at how that works. So the first thing I'm going to do is I'm going to put these things into slope-intercept form. So for this equation, I'll add x. And for this equation, I'm going to add y and subtract 6. So here I have a y-intercept of -2, that's right here, and a slope of 1. So if I go up 1 over 1, that would be my second point. And if I go ahead and graph this line, I'm trying to be as accurate as I can be. So I'm going to move it off a little because I made it a little too steep. And then I'm going to move it into the place where it belongs, right about there. Okay. And then for the second equation, I have -6 as my y-intercept, so that's 2, 3, 4, 5, 6. There's -6. And it has a slope of 2, so it goes up 2, right 1, up 2, right 1. In fact, you can see that I can go up 2, right 1. I'm getting pretty close, up 2, right 1, and that actually looks like the point. So one of the ways to try to avoid the confusion about where exactly are the lines intersecting, because when we're working by hand, it can be pretty imprecise. If I'm using a tool like my graphing calculator or Desmos, it could be a little bit easier, but right now I think I know the answer. And by following slope, it's a lot easier to see if I have that same point. Okay, so this would be 1, 2, 3, 4. So x would be 4. And y would be 2. Let me make sure I did that right. 1, 2, 3, 4, 1, 2. Okay, so this is what we think is the solution. So let's check this now in our two equations. So in this case, my y was 2 when my x was 4. And 2 is equal to 2, so it works in that equation. And when I bring this one down, I'll have 2 times 4 minus 6 would equal 2. So this would be 8 minus 6 equals 2. 2 does equal 2, so that works there. This is indeed the solution of this linear system. When we look at this type of a problem in a real-world sort of context, we can create our linear system based on the information that's been supplied. So what we have here is that there's a business that rents inline skates and they rent bicycles. And you can see the inline skates cost $15 a day and the bicycles cost $30 a day. So during one day, the business has a total of 25 rentals and they collect $450 for the rentals. If we want to find out the number of skates rented and the number of bicycles rented, we can create a linear system that uses the same two variables, x and y, to represent the same thing. So we're going to let x be the number of pairs of skates rented, and y could be the number of bicycles rented. And because we're writing two equations, we're going to look at two things. So the first thing they talk about is how many total rentals they have. Well, I know that the total number of rentals of skates plus the total number of rentals of bicycles will equal the total number of rentals. So they had 25 rentals. And then the other one is about how much money it costs. So I know $15 times the number of rentals they had for the skates plus $30 for the number of rentals they had for the bicycles will equal $450. Okay, so now I've created this linear system. I'm going to take my linear system and I'm going to move on with it to the next slide. Okay, and I remember this was 25, so I missed it on the last page. So if I want to go ahead and graph this now, I would probably go ahead and put these things into, I might put them into slope-intercept form. In fact, the first one, actually I don't really even have to do that. I'm going to graph both of these by finding intercepts. Okay, so when we look at this, I could see that the x-intercept and the y-intercept is 25, and when you think about it, that makes sense. If I didn't rent any bicycles, but I had total of 25 rentals, then I must have rented 25 skates for that. Okay, so let's go ahead and look at this. Let's call that 10, 20, 30, 40. That's probably too far. Maybe we should do this on a slightly different scale. So let maybe 2, 4, 6, 8, 10, 2, 4, 6, 8, 20, and then 2, 4, 5. That would be right about there. 2, 4, 6, 8, 10, 2, 4, 6, 8, 20, and then 2, 4, 6. That would be right about there. So this graph is going to go from here to there. Right now, when we look at the next equation, if I want to find the y-intercepts, to find the x-intercept, I set y to be equal to 0. So I'd have 450 divided by 15, so that would be 30. So here was 25, 26, 28, 30. So that would be right there. And then when I deal with the y-intercept, I set x to be equal to 0, so I'll be 450 divided by 30, and that will be at 15. So here's 12, 14, 15 right there. Okay, and if I go ahead and graph that, it looks like that. Now, what it looks like to me is that my intersecting point is right here. Okay, so let's double check that and see. So this would be 10, 12, 14, 16, 18. So I think x is 18, and then 2, 4, 6. Well, it couldn't be 6 because I need to have, right, I need to have 25 rentals. So it could be 7. Or it could be 19 and 6. So well, let's do 18 and 7, right? Because they have to add up to be 25, and I know it fits that now. So let's see if it fits the second equation. So I've estimated the point of intersection. 18.7 is what I think it is. Let's check whether 18.7 is a solution, and then we'll see what happens. So if I plug 18 in for x, and I plug 7 in for y, it should equal 450. Well, 7 times 30 is 210. And 15 times 18, that's going to be 180 plus 90, that's 100 and, I'm sorry. So it's going to be 180 plus 90, that's going to be 270. So when you look at that, that's going to be 480. So that does not work. Okay, so the other point that I thought might be it, and when you think about it, I had too much money, which probably means that I have too many bicycle rentals. So now let's try 19.6. And it might also be 20 and 5. In fact, in looking at 19 and 6, I'm going, that's not going to work either. I can see, though, that 20 and 5 will work out. So when I plug them in, I know that 20 plus 5 equals 25. When I plug them into the other equation, 15 times 20, that's going to be 300. And then 30 times 5, that's going to be 150, and the whole thing needs to equal 450, and that one works. So this is not the solution. The solution is 25. Okay, so sometimes it's difficult to tell where the actual intersection point of the graph is. And because of the inaccuracy of the way I've made my scale and used my graph, it looked like it was in a different place than it really was. But by testing, you can work out what the exact solution is.